All right, so welcome back. So now we're going to start talking about the formed elements of blood. Okay. Um, so one of the things you're going to notice in this image, I kind of like it. It's a really nice drawing. You got a lot going on though, right? You can kind of see these little guys, these little platelets. You'll notice you have these platelets again here, and they're kind of building this real mesh, and you got red blood cells trapped in it. Maybe if I move myself a little bit here, you'll see it a little better. There's a mesh here, and what they're trying to do is repair. This is part of that clotting, that fibrinogen that we had mentioned in the last lecture. They're trying to repair this tear in the blood vessel, trapping red blood cells so things don't leak out, so plasma doesn't leak out. You see the red blood cells, and then again, these white blood cells you see scattered, not in kind of telling as well. There's not as many white blood cells as there are platelets or even red blood cells. All right, let me just hide myself again so you can see the image a little bit better. So we're going to talk about the red blood cells. We'll give them the more I guess, scientific name of erythrocyte as we talk about them. White blood cells, which are leukocytes, and then platelets, which we will call thrombocytes. All right, so let's just talk quickly about hematocrit. We had seen this image last lecture too, right? We had test tube, and we saw something that looked like this: the plasma, that buffy coat, and then the red blood cells. So when we talk about just the red blood cell part, what we call that is hematocrit. So you see the definition here. It's a percentage of blood occupied by red blood cells. Okay. And as I mentioned to you last lecture too, the amount of red blood cells is going to vary between females and males. So you'll see the normal female range here between 38 and 46%, and they give you the average. And then the male range is a little bit higher, the typical male range, a little bit higher. And this is going to be due to testosterone. And let's see, hopefully I can write better right now. It's due to testosterone. And the reason being, oh, geez, I'm back in the red color again, is because testosterone is going to stimulates a hormone called erythropoietin. Okay, erythropoietin. And this hormone erythropoietin is going to increase the production of red blood cells. Now, something to keep in mind is that both males and females have testosterone. Okay, it's just that the ratio of estrogen to testosterone is going to be different between the two genders, right? So females have a lot more estrogen compared to testosterone, and males have more testosterone compared to estrogen. So basically, more testosterone, more stimulation of this erythropoietin, higher number of red blood cells in males. Hopefully that makes sense. Okay. And you've probably all heard of anemia. Anemia is basically a low number of red blood cells, so somewhere below our typical range for either gender would result in anemia. It's just not enough red blood cells. Oh, and I should also mention one of the other contributing factors for women tending to have a lower red blood cell count or hematocrit value than males is simply the monthly menstrual cycle, the loss of blood during that time. Okay. Okay. And this term right here, polycythemia, basically that simply means too many red blood cells. Okay. So anemia is basically not enough red blood cells, or not enough something called hemoglobin. We'll talk a little about that in a bit. And then polycythemia means that there's too many red blood cells. So the question is, why do we actually care about these hematocrit values? Well, I think The anemia is pretty obvious, right? If you don't have enough red blood cells, and I think we all know this, right? Red blood cells are carrying oxygen. So if we don't have enough red blood cells, we're not going to be able to carry as much oxygen. That leads to fatigue. And depending on how bad that anemia is, it can even be, fairly deadly. Okay. Now, on the other hand, polycythemia. Why do we worry about having too many? Can you think about that? I mean, just think about that for a second. Like, why would having too many red blood cells be a problem? Right? I think it's kind of like that old adage, too much of a good thing isn't good, right? Basically, if you have too many red blood cells, your blood becomes very thick, and it makes it very hard for your heart to try to work, to try to pump this blood. So it can actually cause the heart to give out. Ever so often, I don't know if you guys have ever heard of blood doping in athletes. Sometimes what athletes will do is they'll, while they're training, they'll draw blood from themselves, and then when they go to compete, like the night before, that morning, they'll give themselves a transfusion, so they'll increase their red blood cell numbers. And what ends up happening is, under this exertion of whatever physical activity they're doing, coupled with the thickened blood, they end up having like heart attacks. This has happened in numerous different sporting events. So it is a real concern. Now we will talk about, and we won't really talk about it here. We'll talk about when we get to the respiratory system, about how your body tries to compensate for higher elevations. So so you'll hear this again then, but I'll mention it right now. So basically, if us, we're pretty much at sea level here in Phoenix, but if we were to go up and train in Colorado, for example, and like many athletes do, right? They'll train up at a higher elevation, because basically what that stimulates is going to be an increase in red blood cells, red blood cell numbers. So it'll increase hematocrit, but it's a gradual increase. It's a natural increase. It's not like a sudden shock to the system. And by doing that, again, they have a little bit more red blood cells. More red blood cells means greater oxygen delivery to muscles. So theoretically, less fatigue during physical exercise. Okay. So hopefully that's a good little fun fact for you guys. All right. So how do we make blood? Let's talk a little bit about this. So let's see if my clicker wants to work for me here. All right, so in the embryo, come on, clicker. All right, new blood cells are going to form in the yolk sac. We'll talk way at the end of the semester and during development about the yolk sac. But yeah, when you're an embryo, you have a yolk sac, kind of like an egg, like, chicken egg, kind of wild, but you do. So anyway, blood cells are forming in that yolk sac from the liver, the spleen, the thymus, lymph nodes, as well as red bone marrow. Now you'll notice here the difference between this newborn and in the adult. The thymus is still playing a very key role in newborns in blood cell development, particularly white blood cells. By the time you become an adult, that thymus pretty much shrivels up into like fatty and connective tissue. It's much, much smaller. Now I've got a Radiolab link up on Canvas. So interesting about this thymus. I'll just give you a quick little synopsis of it. So you can see how big this is, right? And you probably have all heard of SIDS, sudden infant death syndrome, right? Well, back in I don't know, I think like the 50s or 60s or so, they thought that it might be the thymus that's actually crushing the air passageway in the lungs of infants, which, maybe, right? It might have been a thing. So what they did was they used radiation to shrink the thymus gland. Well, unfortunately, as I think we all know now, radiation is never a good idea, right? And getting rid of a giant gland like this that's really important, particularly again in like white blood cell development, caused lifelong problems for those individuals. Additionally, one of the things that happened, and I'll kind of click myself back on so you can see me. basically as moms that brought their kids in, and so they're to get the kid to be irradiated, right about here, mom would hold the kid right here. Well, the nasty thing about radiation is when they're bombarding the child, at the thymus with the radiation, it also hit mom. Well, it hit mom in the chest. So you actually saw an upswing of breast cancers in that group of women who had gone through this procedure with their child. And just like to bring this to like your attention too, it's kind of this was sort of, I don't know, maybe fad is the right word. It was a fad kind of very similar to how the anti-vaxxing thing was a fad. Like if you really cared about your kid, you didn't do it, right? Kind of like, the anti-vaxxers, they're like, no, I care about my child. That's why they're doing it, right? They love their kids. It's not like they're trying to hurt them. It's a genuine concern, albeit misguided. And just like the anti-vaxxers, the people that wouldn't, or I should put this, the people that would get this done, this radiation to the thymus, were usually the rich people. So you had like a whole generation, I don't know, I think it went on for several years at least, of individuals who were these rich families who had these kids that were essentially very sickly because of this treatment. Meanwhile, poor kids never could afford radiation, so those people weren't affected. Kind of interesting. Kind of like vaxxers too. You see like outbreaks in mumps, measles, and all that kind of stuff in more affluent communities because those are the people that really bought into the anti-vaxxer kind of movement or could afford to do something about it, I guess. Anyway, I'm going to click myself off and we'll move on. If you are interested, though, take a listen to that Radio Lab. Super interesting. All right, come on, computer. Sorry, guys, I'm having an issue with advancing this slide. All right, so hematopoiesis or hemopoiesis in the adult is going to occur in red bone marrow. So if you remember back to 201, that red bone marrow is going to be found predominantly at the ends of long bones, right? And it's called red bone marrow because that's where the red blood cells are being produced. You have, we'll talk about this when we get to blood vessels. You have a special type of capillary that has very large holes in it. So these newly formed red blood cells can easily go into the bloodstream. And here you can see flat bones, sternum, ribs, skull, pelvis, ends of long bones. Okay, so if I wanted to give you the full story of how blood cells are formed, red blood cells as well as white blood cells, I would show you something like this. Okay, this is a very full picture. It's a scary picture. It scares me, frankly. There's lots of things and there's abbreviations and it's horrifying. But let's just kind of like look at this very generically because I think generically it's kind of interesting. What we'll see here is that everything starts off with something called a pluripotent hematopoietic stem cell. So far you're probably like, all right, all I understood was stem cell. All right. Well, hematopoietic, we just talked about it. Again, that's hematopoiesis. It's just blood cell formation. And when you hear something being pluripotent, I think we all know what potent means, right? Strong, it's viable, right? And pluri, think of like plural, more, like just more. So it has the potential to be many different types of blood cells. Okay, that's all this means. And in fact, what's kind of neat is that this one pluripotent hematopoietic stem cell gives rise to all sorts of natural killer cells, which we'll talk about in the white blood cell, excuse me, T cells, B cells, a whole slew of different white blood cells, as well as red blood cells. Really pretty impressive. And this is just, again, maybe you want to revisit this at the end of the lecture. It'll make a little bit more sense to you. And maybe when we talk about the immune system as well, when we talk about the immune system, we'll really focus in on all of this. And hopefully the letters and stuff won't be so scary. Anyway, I guess the point being, again, we start off with this pluripotent hematopoietic stem cell, and it basically gives rise to all those other cells. So let's just focus in on red blood cells, because that's kind of where we are right now. Let's talk about its life cycle, right? They get old. They don't live forever, right? So we have to recycle them. That's what you're seeing here. Here's this big old monocyte gobbling it up and it's going to basically recycle its parts. Red blood cells, due to all the travel that they do and all the work delivering oxygen and carbon dioxide and acting as a buffer, live only about 120 days. Okay, typical red blood cell. Okay. They also have to do a lot of bending, which kind of accounts for their shape. They kind of have that biconcave disc kind of shape to them. They have to bend and fit through capillaries. So after a while, they just like any of us, keep doing something for too long, you kind of wear out your joints. You wear out red blood cells as well. Okay. Now, red blood cells do not have organelles. So that, the things that we normally take for granted, like the Golgi apparatus, the endoplasmic reticulum, nucleus, any of that, there is none. There is none. No mitochondria, so it's no organelles. So basically, and remember, those organelles, no ribosomes, those are all the things that help repair cells. So once it's damaged, it can't repair itself. Okay, and that's what you're seeing in this image. So this is an image of a macrophage, which is a cell that basically gobbles up other cells. So these worn out cells are going to be removed by these macrophages in the spleen and in the liver. And then this term fixed that you're seeing here, so these are fixed macrophages, and that simply means that they are found in the spleen or in the liver. They don't move around. They're fixed. They're in one spot. Okay, and like as I mentioned, the breakdown products are recycled. Now, I want you to think about something for a quick second. Why don't red blood cells have organelles? Why don't they have a nucleus? Why no mitochondria? Any ideas? Well, so they can bend and fit through capillaries. Well, true. Okay, that is true. Can you think of another reason? How about something to do with their main job, right? What's their main job? To transport oxygen, right? All right. Well, if you have a cell that is transporting oxygen, the last thing you want to do is give it things that are going to need to use up the oxygen it's transporting, right? It doesn't make it a very good transporter. It's kind of like giving your dog the steak to bring to the dining room table. It's never going to happen. It'll eat it, right? So basically, red blood cells, everything that could possibly use up the oxygen that they need to carry has been taken out. So all they can do is transport it. They can't actually use it. That's kind of neat, right? So they make the ultimate carriers for oxygen, but unfortunately, they can't live very long. All right, so let's go on and take a look at how they're actually recycled. So let's start up here. So they've been in circulation for about 120 days, right? And then as they're traveling through the bloodstream, eventually they'll make it, to either the liver or to the spleen, or even sometimes in the red bone marrow. You'll find some macrophages there as well. Okay, so you can see here in step 1, the red blood cell just basically wears out, it's old, and it dies. And then it's phagocytized. That monocyte or that macrophage, I should say, will come and gobble it up. And then it gets recycled. So the main part of red blood cells is something called hemoglobin. Okay, so that hemoglobin, and we'll talk about a little bit more about it in a second, that hemoglobin is going to get split into two. It has two components. There's a globin part and there's a heme part. Okay, now the globin part is simply protein, and proteins, the building block of proteins, are amino acids. So simply the globin gets broken down to amino acids, and then those get reused for protein synthesis, right? Make some new kind of protein, whatever that protein might be. All right, well, that's easy. Then the other part, the heme part, has a little bit more of a long cycle. Okay, there are two parts to a heme. Okay, again, there's a protein part, and then there's going to be the iron, right? So I'm going to backtrack one more time, repeat myself. So red blood cells, there's two major parts to the hemoglobin in red blood cells. And again, that's the vast majority of what red blood cells are, just hemoglobin. You have the globin, and then you have the heme. Okay, again, the globin is just protein. So its building blocks are amino acids. They just get broken down and reused as other proteins, whatever that other protein might be in the body. The heme part has two parts as well. In heme, you have the iron, which as you're seeing here is Fe, and then you also have a protein part, which is essentially broken down to what's known as biliverdin. Okay. Now let's just kind of track the iron part first, because they're going to get processed differently. Now, iron, if left all by itself in the bloodstream, is very destructive. Okay, so you never see it just floating unaccompanied by something else. It's almost always bound to some other type of protein. So in this case, the heme, when we take the iron out of it, it is going to be immediately bound to something called transferrin. Okay, and that transferrin is going to help transport the iron to other body parts, particularly the liver. You may have heard that the liver is an iron-rich organ, and it is. And then in the liver, it is stored, again, bound to a protein as ferritin. You can never leave it alone. Again, it's very damaging. And then as the body needs the iron to produce more red blood cells, it'll get transported from the liver to the ends of those long bones or the flat bones, wherever the red blood cell formation is occurring. And again, it gets attached to transferrin, where it then gets shipped to, again, the red bone marrow, and then it's bound with globin, some vitamin B12, the erythropoietin, which is that hormone that helps stimulate red blood cell production, and we form a new red blood cell. Okay, hopefully that made sense. So again, red blood cells, two parts, hemoglobin. Globin's easy, it's just protein. It's broken down to amino acids, and those are reused to make new proteins. The heme part has two sort of subparts to it. The iron part never is left alone. It's always bound to a protein. Whenever you're transporting iron, you see here as we're transporting it to the liver or from the liver to the bone, we're going to bind it to transferrin that keeps it from damaging other tissues as it's being transported in the blood. Predominantly the kidneys is what we care about. It can absolutely destroy kidneys if iron is not bound to this transferrin. When it's stored in the liver, it is bound again as ferritin until it's again shipped to the red bone marrow, where then it combines with globin, vitamin B12, some erythropoietin, and we form a new red blood cell. Now, this biliverdin part of heme is quickly converted into a more stable metabolite called bilirubin. Okay, so biliverdin is quickly converted into bilirubin. That bilirubin is sent to the liver, where it's actually incorporated in bile. You see that green arrow. So it's put into bile. And then that bile is basically released into the small intestine, more specifically into the duodenum of the small intestine. As food will travel through the small intestine, as this bilirubin, excuse me, once it gets to the large intestine, there bacteria in the large intestine will convert the bilirubin into something called urobilinogen. Okay, now this urobilinogen will be reabsorbed into the bloodstream. You can kind of see this red arrow here, and it does get transported in the kidneys, where it is once again converted into something called urobilin. And that urobilin is yellow in color. It is what gives urine its yellowish color. Okay, particularly that really dark, like yellow color. Okay. Now, the part of the urobilinogen that is not transported into the bloodstream and stays in the large intestine is then further converted into something called stercobilin, and it is what gives gives feces that brownish color. Okay, so there's quite a bit of processing that biliverdin undergoes. So again, it is released from the heme as biliverdin, quickly converted to bilirubin. That bilirubin is transported in the bloodstream to the liver, where it is incorporated into bile. The bile is released into the small intestine. It travels through the small intestine, making its way to the large intestine. In the large intestine, bacteria will convert the bilirubin into urobilinogen. Some of that will get reabsorbed into the bloodstream. It gets taken to the kidneys, where it is transformed into urobilin. and it's released in the urine, giving it its characteristic yellow color. That the urobilinogen that is not transported to the kidneys is converted into stercobilin, and it's basically lost in feces, and it's what gives feces that brown color. So that's basically how we recycle the hemoglobin that is found in red blood cells. It's basically how we recycle red blood cells, because again, red blood cells, vast majority of them is hemoglobin. All right, so I know that's quite a bit, and I don't want to have this lecture go too long. So I'm going to stop this here. We're going to finish up on red blood cells before I move on to white blood cells in the next lecture. Please, if you have any questions, let me know. I will be more than happy to answer any of your questions via email or in person. All right, see you next time.